Welcome to another GC Basic demonstration. This is part 7 for the 18xxQ24. This is part 7 of a 20 series set of videos to really showcase how the Q24 works with GC Basic. So, like and subscribe to the video. If you don't like and subscribe, the metrics on YouTube, people will search and they won't find this video and watch it all the way through, because that is another important metric. So what we're going to do is, using the switch that we've seen before, the ADC, we're going to make the LEDs flash in sequence. And when we push a button, they're going to reverse. This is the classic microchip low pink out board demonstration. This was the one that was always installed, but they didn't really go through the 6 steps that we've been through to say this is how it all works. So we're doing that now, and then we'll actually just use this as a baseline to introduce serial in the next video. I'm assuming you've got everything installed. Programmer works, etc., and I will show you my board at this point. This is my board, hasn't changed. And when I push this switch here, as of, I can't remember where we were yesterday. Yeah, this is the board as it was yesterday, and we'll get it all working. So I've got 4 LEDs here, a potentiometer here, a switch down here. What else have I got? Oh, microcontroller up here. There we go. I've actually got the reset attached as well still. So, oh, there you go. That's the reset lock. Okay. Oh, that's what we were testing last time. The reset button. There you go. Still works as I left it. So what we're doing, we're going to put that all together. We're going to have the LEDs rotating in sequence. The switch will be controlling the direction of the sequence. It'll be going one way or the other way. We'll be using master clear as an input, not as a reset, the default. We're going to read the ADC voltage from the potentiometer, and that will adjust the time using the weight, and it will give it consistency. And it's consistent across all the microcontroller frequencies. So that will then recalculate it, etc. Quite a simple thing, because what we're going to do is just initialize things. We're going to flash a chip, flash the first LED, then do a forever loop forever, okay? And we're going to read the ADC. We're going to do some weights based upon that, and then we're going to see if the switch state has changed, and we're going to move left or right, and we're still going to set the state of the LEDs, but we're just going to have to handle it differently because of things that we have already learned. We've already learned that if you rotate in one direction, it's going to use the carry. So we have to use the carry a few times to sort this all out. But we're going to set various little bits, and we're just going to carry on around this loop going, has the switch state changed? Go left, go right with this delay. In terms of the hardware, prototype board you've seen, 5 volts, programmer, LEDs and resistors, switches and a resistor, and that's the diagram we'll see in the program. So let's go directly into the code, and I'll go into GC code, and this is where we left it yesterday. I will shut that down with Control W and get rid of that, and then the one I'm using is 090 or 90. And let me have a look at it. It's called reversible LED with variable delay. There you go. That's the function we saw previously. Let me have a look let's go back to the top. Let's walk the code. Control B to get rid of that little input window. So let's zoom in and see what we've got. So we've got option explicit and our chip defined here. And what we're going to do, we'll actually put that at 64. That is the default. And we can see that in the compiler results. We'll check that out in a minute, okay? You've seen all this. This is all the constants and just setting all the ports as output. So everything sort of down to there is all about setting up the hardware. Now you can see that you can actually use the editor to get rid of a lot of stuff, okay? Now here's the program. Seen a lot of this before, okay? So we've got some variables, one called direction, and that's a bit variable, and it'd be either 0 or 1, and it will just tell us which direction we're moving in, left or right. Then I've got a constant below that. If you note, one's called LED right, one LED left, 0 or 1, and I set direction to one of those, and it will move left or right, because we'll lose that later on. I have a delay variable, which is just essentially the variable that will be our wait signal, and then the port state. And I'm going to set the port state to 1 because that will set the first LED on, and that's just to set up the initialization. And then we've got our program. I am not going to look at the function. It's the same function. Right, it's going to calculate the delay. How does it calculate the delay? Read AD and scales that result. And all it does is scales that result to 50 milliseconds to 1 second. Read AD works. We saw that earlier on. We set the LED port called lat-B to the state of our variable called LED port state, and I'm only setting the top 4 bits, the bottom 4 bits. Why? Because if the other 4 bits are in use, I don't want to be changing them. So leave those as they were. So I'm making sure that I'm not changing things inadvertently. And there is a better way of doing this, I'm sure. But I just want to make sure that you consider the other 4 bits. And this is a very simple way of doing it. I think it would be better if you read the port in first to get the top 4 bits out. So you'd actually do it slightly differently. But it's a good, GC Basic will handle that for you. Okay, then we wait. Let me just put that in there. Manage the key press. Then we got a delay. This just proves I write the code just before I demo. Manage the direction. Okay. So if the button's been pressed, it will change the direction. What does that mean? If the key press is true, direction equals not direction. Well, if it was a 0, it will set it to 1. If it was a 1, it will set it to 0. It's a not statement. So that's the exclamation mark is the same as writing not. And here we go. If the direction is left, then do something else. And then you can assume the else is obviously LEDs moving to the right. Which one's the easiest to explain? Well, let's assume that we're rotating to the left. Okay, that's the first way we're going. So we're expecting things to move the LEDs in a leftward direction. Therefore, we're going to go from a value of 1, 2, 4, 8, 1, 2, 4, and 8. Therefore, we will rotate things to the left. But if you did that on its own, it would do it once and it will stop, because it will go 1, the bits will go, the first bit, or bit 0, bit 1, bit 2, bit 3, bit 4, bit 5, bit 7, overflow, and chaos ensues. So you have to put a test before that to say, okay, if the LED bit number 3 is set, it's equal to 1, then we just have to reset the port, our little tracking variable, and make sure that we set the clear. And we're going to use the clear register, or this register.0 now, this clear, the carry flag, the carry flag. We're going to use the carry flag to our advantage. We are going to put and set the carry flag to 1. And then when we rotate to the left, guess where it puts it? It puts it in bit 0. Brilliant. So look, set the LED state to 0, but set the carry flag, you get a consistent rotate. It moves it into bit 0. Else, if that top bit's not set here, bit 3 is not set, clear the carry flag and just rotate. And if I show you that running, compile that up, I'll go to Zen mode so you can see it work. The LEDs are moving exactly as we thought. So when it gets to the end, that's bit 3, sets the carry flag and then rotates the carry flag into bit 0. Genius. What happens when I push the button? Moves in the other direction. Stunning. How does it do that? Let's look at our code. We're now moving to the right. Well, that's easy. Moving to the right is simpler because we make sure the carry flag is set to 0 and we rotate to the right. Now, because we cleared the carry, we can test if the carry flag has actually been, if the bit has been moved or been carried forward. So if bit 0 was set in our variable and we rotate to the right, it will set the carry flag. And then we can set our top bit to 1. So we're making this rotation work for us in a favorable manner. And to be quite frank, if we look at the assembler for this, it is very simple. It's just a concept in your mind. So I haven't shown you the switches. Why? Because the switch stuff is simple. I can rotate this potentiometer and things will get faster. And then it's flashing away in the camera. And then it goes, it's a bit too fast for the camera there. If I push the switch, it's definitely moving in the other direction. Really quite simple. But we put together all that we've learned. And if I push the reset button, what happens? Nothing, because I'm not actually addressing that in this program. It's just set. I did that as reference. Oh, look. So here's the 1 minute, the 1 second delay. Now full on. Push the button, and it goes in the other. Push the button, and it goes in the other direction. Here we go. Brilliant. It worked just like the low printout demo. So what we're going to do next in the next video is we're going to introduce serial, and we're going to put the values that we're seeing on the screen here on the LEDs onto a terminal so we can actually see what's happening. But I want to show you one other thing before we go. Let me just shuffle things around on the screen. Here, in this window here, we can see the compiler. We can see the results. It said it compiled it in a certain amount of time. It then programmed it. That's not what I want to show you. I want to show you in the preferences editor how you can see more information and the value of that information. So, function key F4 in the IDE. Type in prefs, edit preferences. If you go into the compiler tab, put verbose mode on. Okay, it might already be on, but I just need to go through to make sure that we're on the same page. Now we're going to recompile that and we're going to look at the results in some detail because it's quite important. I'm going to press make the hexadecimal file. I'm not really interested in the programming cycle. I'm bringing up the whole of that bottom window to show you the full extent of what it's just done. So at the top here, it says I've executed a command and it gives me the build of the compiler. We might ask for that. Then it says I found all these source files, starting with your source file. Then all the files it found in the compiler tool suite. And that's this set here. There may be more. It depends. You can see there's a whole long list here. But what I want to do is examine this set here. So I'm going to zoom in and we're going to examine that set. Just going to move the window around a little bit. There we go. So what you've got is it's compiled 65 lines of your code, user code, and there's one subroutine. Subroutine is also a function. And out of the 475 system routines, it used 11 in total. There are many, many more than that, I assure you, but for this particular configuration. How much memory did it use? 2.2%. How much RAM? It used 45 bytes of RAM, and it used the internal oscillator at 64 megahertz. It clearly shows you that. And it used GCSM. Why is this important? Because if we go back into our program and we change the frequency at the top to, I've changed it to 1. You'll have to, I've changed it to 1 at the top here. Right there, look, 1. Recompile. We want to look at the result now at the bottom. It says that it's now used the internal oscillator at 1 megahertz. And if we look out on the camera, Zen mode, it's doing exactly as it was before, 1 second, full on, exactly as we left it. And if I tweak that back to 50 milliseconds, it was because it's recalculated the weight on your behalf. If I turn the right potentiometer, there we go. There you go. But let's look at what happens if I do something slightly different. Let's assume I put 48 in here, and I'm doing this blind because I can go and check whether this is a valid frequency by looking in PIC info. 48 is valid. It's quite valid because it's actually an internal oscillator. I just want to pick a frequency that's not. Let's pick 20. It's quite a common oscillator, but does it use the internal? No. 20 hertz. It's not a primary internally oscillator. And just so that you can see it in the background, you need to go check now that the clock source is correctly set up. So now you'd have to go and change the configuration, ensure that your oscillator is set up correctly. You may need a high accuracy external oscillator, but GC Basic tells you to go and go make sure that is set up. We can't do that setup because we don't know what your setup is, but you'd have to change the configuration to suit your setup and ensure your oscillator is operating. But you can always fall back to the internal oscillator just for testing. Wanted to show you that. I will put that, get rid of that setting there. We'll leave the camera, we'll leave the board like that, and then we'll change and add some serial into this program later on in the next demonstration. And with that, we're going to use that serial to display the values from the ADC from this program. Enjoy.